Properties of definite integrals. First property says that if you're trying to integrate a function with respect to x from a to a, meaning the interval that you're trying to find the area of, so there's a function, and if I'm trying to evaluate the definite integral, I'm looking at the area from a to a. It doesn't actually create an area. It's one-dimensional. There's no second dimension because we don't have any distance here to get to a b that opens that up. So, no area means you get 0. The second property says, well, what happens if I switch the upper and lower limits of integration? So instead of going from a to b, I go from b to a. Well, it turns out that what that does is it gives you the exact same area as you would get going from a to b, except negative. The third property is the constant multiple property of integrals, which turns out to work exactly the same way as you'd expect it to. So if you're trying to integrate a function from a to b with respect to x, and that function is being multiplied by a constant c, it is totally fine to pull out that constant c, to integrate, and then multiply your answer by c. The fourth let's say when we are integrating that we're integrating the sum of two parts, and this is for a definite integral. It works exactly the same way as an indefinite integral, where you can evaluate the first function from a to b, and then you can evaluate the second function from a to b, and you can add the two results together. The very last rule or property says that if you're evaluating the integral of a definite, or the definite integral from a to b of a function, that you can split that up into subregions. So for example, I can go from a to p and evaluate that function, and then go from p to b. And splitting it up into those two sub-functions is the exact same thing as evaluating it as a whole. So this sort of speaks to what we did when we were using geometry to calculate the definite, or to evaluate the definite integral, where we split it up into sub-intervals and calculated the area of each region and then just added them up. So what you want to imagine here is that you have some function and you're finding the area under the curve from a to b, so from here to here. And if you have an in-between value of p, it's perfectly fine to find the area from a to p, and then also find the area from p to b, and then add those two areas up, and it definitely represents the whole. All right, that'll do it for this section.